I thought it was kind of apropos to start out the lesson talking about, or kind of showing you possibly what it might be like to be in an earthquake. Now, obviously, the ground wasn't shaking, it was me shaking the camera, but on your end, it might have simulated kind of what it might have looked like to be in an earthquake. So let's dive in, right? An earthquake is the ground shaking, for lack of a better term, right? Movement in the ground that are caused by a sudden release of energy along a fault line, right? Most earthquakes occur on the edges of the plate boundaries, right? So on the edges of continents, or on the edges of these these tectonic plates, the edges are where 99.9% of the earthquakes occur. Okay? Why do they happen? Well, you've got to remember, these aren't smooth plates rubbing past each other or banging into each other. They're jagged, misformed rocks, and they're building up pressure. So as the pressure builds up, eventually the pressure overcomes the friction, and they give way very quickly. Right? So rocks on both sides of the fault are pressed so tightly together, this creates a massive amount of stress on the rocks. This stress is caused friction to keep the rocks locked together in place. Until the stress becomes greater, then it overcomes the friction, and suddenly the rocks grind past each other. And that's the shaking of the ground, is the grinding past each other that you experience. Okay? Where do they typically occur? We just talked about it. Around the edges of tectonic plate boundaries where two plates meet. That's typically where they occur. Now, they can occur in other places, right? There's earthquakes on the Hawaiian Islands, right? A hot spot. There's earthquakes in the middle of the United States, in Kansas, I believe. There's some issues that they're having there, but that's in the middle of the plate. But 99% of the earthquakes occur around the plate boundaries. Why do they happen? Massive amounts of stress build up between the two plates, and eventually the stress is released, what we just talked about. How do scientists locate the edge of a plate boundary? Well, you plotted all of those earthquakes and volcanoes, and you came up with this blank map that had these earthquakes and volcanoes, and you were able to draw some lines, specifically the Ring of Fire, but all plate boundaries could be drawn from looking at these earthquakes and volcanic data. Right? So it's where the highest number of earthquakes and volcanoes occur. That's how we can identify where the plate boundaries are. Okay, so we've talked about this thing called seismic waves, right? These are the waves that are created from earthquakes. They're released when the earthquake occurs, and they travel outwards in all directions. Just like if I threw a rock into a lake, those waves radiate outwards in all directions. They travel out in all directions. They like the wave they create, like the waves created when you drop a rock into the pool. They travel out in all directions, just like you toss a rock into a pool and it radiates out in all directions. Okay. What scientists can learn from these waves? They can learn a massive amount from these seismic waves. Number one, we've never been to the center of the Earth. So these seismic waves are the only way that we can study the center of the Earth, and specifically the mantle, the outer and the inner core. We've never been there, so we have to rely on scientific data of these waves. As an earthquake occurs, these waves pass through the Earth, and then seismographs on the other side get that information, and then different scientists can compare them and study the inside of the Earth, right? They travel at different speeds throughout different mediums, and therefore scientists can study the interior of the Earth, the composition and temperature, by measuring the speed changes in the waves as they travel through Earth. They can also find the focus or center of the quake as well, right? And we talked about that in class. We take 3 different seismograph activity sheets, and we compare the data, and we triangulate where the strength is, and we can find the center of the earthquake. Let's take a look at this link, see what it's talking about.
Earthquakes generate 2 main types of seismic or shock waves: body waves and surface waves. Body waves travel through the interior of the Earth. The fastest of these are primary or P waves. These compressional waves move faster in dense rock and slower in fluids. Thus, their speed and direction change. Because they are deflected by the Earth's core, P waves are not seen in the so-called shadow zone. The slowest body waves are secondary, or S waves. S waves are elastic shear waves that move material sideways at right angles to their direction of travel. Because secondary waves travel only through solids, they do not penetrate the Earth's outer molten core. For this reason, there is also an S-wave shadow zone.
So if we go back and look at this picture does a really good job at showing you every time a seismic wave hits a new medium or a new material, it changes speed and direction. And you can see that as this wave comes through the mantle and hits the outer core, it changes direction. And then it travels through the outer core, and then it exits the outer core, and again, changes direction. And so you've got this different direction and speed changes that scientists can take that data and study the inside of the Earth, because we've never been there.
The slower seismic surface waves do not penetrate the Earth's interior, but follow the surface. One type of surface wave, the love wave, travels in a circular motion and causes damage by displacing materials horizontally. Love waves can be very damaging. This cracked pavement and these twisted railroad tracks clearly demonstrate their destructive power. Earthquake damage also results from Rayleigh waves, surface waves which deform materials vertically.
All right, so we're going to get into the different types of waves, but scientists can use them to study massive amounts of information deep within the... So we classify into two different types of waves. First, we've got what are called body waves. Now, within body waves, there are two types of body waves. There are P waves and there are S waves, okay? P waves stands for primary waves. They are the first waves to show up on the surface or at an earthquake site. They're the first ones, they're the fastest, and the first to be detected. They're compressional waves. Particles move back and forth in the direction of the wave. So for example, right, if you take a slinky and you stretch it out and you just compress it and let it go, you're going to get compression of the ground in some areas and you're going to get expansion of the ground in other areas. That's a P wave. It's moving the material in the same direction that the wave is traveling. Okay? That's a P wave. This wave can travel through solids, liquids, and gases, so it can travel through the Earth's core and come out the other side. The second type of body wave is an S wave, and these are the secondary waves to show up on an earthquake site. They're the second fastest. Rocks move side to side or perpendicular to the direction of the wave. So S waves, the wave is traveling in this direction, but the ground is moving in the perpendicular direction. Okay? And these waves can only move through solids, right? So, again, the P waves, the direction of the wave is in this direction, and there is compression, and expansion in the direction of the wave. In an S wave, the wave is traveling in that direction. The ground moves perpendicular to the wave motion. Okay? Two types of body waves. All right? Now, the second category of waves is called surface waves. These are waves that travel along the surface of a body, not through the middle. And they are the slowest, but can cause the greatest damage. There are two types. There are L waves. L stands for love. Okay? It's so apropos to be so close to Valentine's Day talking about love waves. Well, it doesn't give a whole lot of love to the land, right? Most of the structures are severely compromised when these love waves come through, right? So rocks move side to side, perpendicular to the direction of the wave. But you can see that from this picture, I know it's hard to see, but we'll show it in class, that the land is also distorted slightly as well. So these love waves are extremely damaging. And then we have these, I call them Raleigh waves. Other people might call them Rayleigh waves. The ground moves with an elliptical rolling motion, or you saw in those videos where the pavement went up and down. Those would be Raleigh waves or Rayleigh waves. causing undulation, just like an ocean wave goes up and down, right? Very, very devastating waves to interact with. So we've got body waves, P and S. We've got surface waves, Love waves, and Rayleigh waves, or Raleigh waves. Okay? Now, recording earthquakes, how do we look at this data? How can we measure them? Right? Well, we've got two different things. We've got what's called a seismograph, which is an instrument used to measure the ground vibrations, and then we have a seismogram, which are the recordings of the vibrations in the ground from the seismograph. So the seismograph is the machine, and then the seismogram is what's produced after an earthquake. Right? It's that comes across and it shows you this moving needle, right? That's a seismograph, and it's creating a seismogram. All right? Now, we can take that data and we can interpret it to find the magnitude of an earthquake, the strength of an earthquake. The greater the magnitude, the greater the ground movement there is. Now, what you and I are used to is this thing called the Richter scale, right? The Richter scale, older method used to measure the ground to find earthquake strength. Now, what we use is what's called the moment magnitude scale. It's a newer, better way to measure earthquake strength. Let's take a look at this video.
Earthquakes are now reported as moment magnitude. So what happened to the Richter scale? Charles Richter and Benno Gutenberg developed the first magnitude scale in the 1930s to quantify earthquakes by relating the size or amplitude of seismic waves, shown on the right, plotted against distances calculated from S minus P arrival times, shown on the left. Connecting the two gives you the Richter magnitude. The scale is logarithmic, so a 1 unit increase in magnitude corresponds to 10 times larger amplitude. The limitation was that seismologists measured certain frequencies, which meant that the signals from large earthquakes weren't adequately represented, like not being able to hear the bass notes on your laptop speaker. That meant that the Richter scale underestimated the size of large earthquakes. Seismologists have since developed far more sensitive seismometers that, with faster computers, have enabled them to record and interpret a broader spectrum of seismic signals. These improvements allow them to better determine the energy released by large earthquakes. In 1979, they connected the seismograph recordings with the actual physical displacements that occurred during an earthquake. The result was the moment magnitude scale. Seismologists no longer look at only...
All right. That's probably pretty good for showing you what I wanted it to show. Hi, Meredith. All right. So that's kind of an updated measurement or a scale that scientists use to measure earthquakes now. Really, the Richter scale is not specifically used anymore. It's a moment magnitude scale. And the other one we talked about in class was the Mercalli scale, which is, again, an updated scale that some communities use and some scientists use. But the moment magnitude scale is a much more accurate way to measure. Okay. Now, how do earthquakes affect us? Well, number one, loss of life, right? A building crumbles, you're going to have loss of life. Okay? And number two, the tsunami that's created after an earthquake, just like the one in Japan, just like the one in Indonesia in 2004, right? The tsunami really can cause a massive amount of loss of life and property damage. This occurs when the ocean floor suddenly drops or rises and therefore sends a wave into two directions. Destruction of buildings, gas explosions, water pipes break and flood, so on and so forth. So I'll show you these tsunami links in class, but understanding that earthquakes can cause tsunamis. Okay? And then seismic gaps, right? How can I understand these things called seismic gaps? Basically, when an earthquake happens, the entire fault line doesn't move, right? The entire thing doesn't shift. Only a portion of it does. And so what that does is that it builds up stress in other parts of the fault line that then could, later on, have an earthquake occur in that location, right? So we have these things called seismic gaps, right? An area on the fault line that has had relatively little recent earthquake activity, but has had a lot of activity in the past. Some scientists believe that these gaps may be where future earthquakes are going to occur. Right? Now I've given you kind of two different pictures. One is of Mexico, but it's the San Andreas fault line, and then we see California. And each one of them, it kind of shows you these seismic gaps. And right here, there's these different shaded oblong ovals are seismic gaps where there was some earthquake activity before, but now they are relatively silent. And that could be a place, or possibly right here, could be a place where future earthquake might occur, because there's probably some buildup of pressure, because there hasn't been any earthquakes to release the pressure. Okay. That does it for your earthquake notes. I hope you paid attention, and you better have wrote down some questions, thoughts, comments, ideas on your paper, because we're going to talk about it on tomorrow. All right. This goes out to my 4th hour homies. What up, y'all? Peace out, home skillets.